Ladies and gentlemen, good afternoon. We are busy with a chapter on transient heat conduction. The work is based on the textbook of Cengel and Ghajar that we are using. I think it is lecture 5 or 6 approximately today on this chapter. We've started by looking at what is transient heat conduction, and I've showed to you it is when the temperature changes as a function of time, and there are many practical applications like that. Then from first principles we have derived a solution for the so-called lumped system. It's a very easy solution, however it has limitations. The limitations, in many cases, we can use the Biot number to help us to make decisions if we can use the lumped system or not. Unfortunately, many applications we cannot do with a lumped system approach. So in this textbook, we've started with the most simple and then we make it more complicated. So the next stage in increasing the complexity would be to look at more simpler geometries. And 3 very special simple geometries were considered in paragraph 4.2 in your textbook, and it's still the paragraph that we are busy with. And it is the plane wall, it is the cylinder, and it's the sphere. And from first principles, we've derived an equation that describes the temperature distribution through those bodies. Unfortunately, that equation is a little bit complicated to solve, and the result of that is presented in table 4.1 in your textbook. That is the complete result, but then there are some easier cases or cases where assumptions were made. For example, if you're interested in the temperature in the center, or for the cases when tau is larger than 0.2, where you only have to use the first term. Okay, so that we've done, and we've done an example. We've done the example of the carcass, the beef carcass, which was a temperature at 37, which was then decreased in terms of temperature in an environment of -10. And we've used an analytical solution. Now, you will also see in your textbook there's also a graphical solution, and that is called the Heisler charts. And I'm going to show you today how you can use the Heisler charts. So if you go and look at those charts, then you will see typically, and there are 3 sets of charts in your textbook. They're called Heisler charts. And there's one for a plane wall, there's one for a cylinder, and there's one for a sphere. And on all of them, they are actually very user-friendly in terms of the use. So for example, for the cylinder, they will give you a sketch like that. Okay? So that is the second graph in your textbook. And on it, they will show you typically the coordinate system, that is equal to R, and the radius would be equal to R0. And then they would also show next to it, there's the environment temperature, and there's the heat transfer coefficient. Okay. And on this axis, typically with the first graph, they have theta 0. What is 0 again? 0 means in the center of the body. Where would that be? That would be at that point there. So that is 0. Okay. So theta 0 would be equal to the temperature at point 0 minus T infinite, the environment temperature, divided by Ti minus T infinite. So Ti, the initial temperature. And on this chart, on this axis, it would have tau, the non-dimensionalized time, which is equal to alpha T divided by R0 squared. Okay. For those of you who have your textbooks here, please open it here. It would be a good idea to take a look at it because we are going to use it in a while. Okay. Now on this chart, there are many lines, and I'm not going to try to put them in. But you will see these lines are lines for a constant Biot number, and in this case they are presented as 1 divided by the Biot number. So 1 divided by the Biot number is equal to K divided by HR0. Okay, so that is the first graph. It gives us, therefore, the center values. Okay, all the values here on the center of the cylinder. The next graph gives us the temperatures at other positions. So that would be equal to theta divided by theta 0. And that would be equal to the temperature at any point R minus T infinite divided by the center temperature minus T infinite. And on this axis now we have 1 divided by the Biot number, which is equal to 1 divided by HR0, sorry, K divided by HR0, something like that. Okay. But the lines now are lines for different values of R divided by R0. Okay. So that is typically the graph, or two of the most important graphs. We're going to get to the other one just now. Now let's suppose I ask you to determine the temperature at that point there. Okay. Let's call it point 1. Okay. So point 1 is a function of R. It is not on the center line. So that would then represent the temperature at point 1. Okay. And we will have to look for the line of R1 divided by R0. Okay. And that would give us the solution. However, you will see the problem is you can only do it if you have the center temperature. So normally, if the center temperature is not asked, the logical thing to do is to first get the center temperature. Okay. So if you look at this graph, okay, you can calculate the Biot number if the environment conditions are given. The radius, of course, is given. You want it maybe at 3 hours or something like that. So after 3 hours, you can go and get the non-dimensionalized time. You can get the Biot number and you can get the center temperature. Once you've got the center temperature, then you can put it in there and you can get the temperature at any point you're interested in. So it is a very easy solution on a graph. The other solution, or the other graph, would be Q divided by Q max. The previous lecture, we've looked at Q, the amount of joules which is being removed out of the body, and that graph would be equal to, on this axis, Biot square multiplied by tau, and the results would be given for different Biot numbers, which is equal to HR0 divided by K. Okay. Do you see? Okay. Okay. Now, these graphs were obviously very important 30, 40 years ago when people didn't have calculators, because it was very, very difficult to solve the solution in table 4.1. Now, I do not say that this is not important and you should throw it away. I use it a lot because the sensible thing to do in many cases when you do calculations, it's very easy to get an answer, but it's just as easy to make a mistake somewhere. So I would do the analytical solution, but then I would just do the graphical solution also and check if it is approximately correct. The graphical solution, of course, cannot be that accurate. In many cases, you'll see when you start using it, it would be very, very difficult in many cases to get the exact point on the graph. Okay, so Tamarin, if you can maybe look at the laptop for us. Let me see if I can show you that. Okay, so that's typically the graph and it's on one page. And I don't know if many of you can see it, but that is what I've drawn there on the board. Okay, now the first part, the top part, looks like that. So I think it's a little bit bigger now. Okay, so I didn't draw in all the lines there, but in principle it is exactly what I've showed you on the board. Okay, and the second and the third graph is just below, and that is how they look like. Okay, so you will see three sets of graphs which are called Heisler charts, which can be used to determine graphically an approximate solution. Let's go back to the previous problem that we did in terms of the beef carcass. Okay, we have said we can assume it's a cylinder, and the diameter is 240 millimeters, and the height was 1.4 meters. And it was given to us that the initial temperature is 37 degrees Celsius. The mass is 65 kilograms. The thermal conductivity K is equal to 0.47 watts per meter Kelvin. The alpha value is equal to 0.13 multiplied by 10 to the minus 6 meters squared per second, and the Cp value is equal to 4180 joules per kilogram Kelvin. Okay. So that was the properties of the body. Okay, what was also given to us is that the environment temperature suddenly changes to minus 10 degrees Celsius. So we put it in the refrigerator. The velocity of the fans typically in that room would be about approximately 1.2 meters per second. And for that reason, the heat transfer coefficient is a little bit higher. If there wasn't fans, it would typically be approximately 10. Okay. So in this case, it was now measured or determined as 22 watts per square meter Kelvin. And remember, it doesn't matter if you use Kelvin or degrees Celsius. We always work in temperature differences. The temperature difference in degrees Celsius and in Kelvin are exactly the same. So you can write it as per Kelvin or per degree Celsius. Okay. So now let's see if we can use this graphical solution. And if you can just go to the slide again. Cameron, if you can go to that one again quickly for us. So that is the first graph. I don't know how many of you have your textbooks here and how good your eyes are. Okay. But on the vertical axis, we have theta 0. Okay. So theta 0, and you don't have to remember it, it's given there. Theta 0 is T0 minus T infinite divided by Ti minus T infinite. Okay, now just coming back to what was asked to us. We were asked to determine the time for the center temperature to decrease to 4 degrees Celsius. Remember that? How long will it take to go to 4 degrees Celsius? And let's call that time T1. And then at time T1, what is the temperature on the surface, on the outside? Because freezing is an issue. It's very important. Temperature shouldn't drop below 0 degrees Celsius. So there's Ts. So let me just use different colors maybe to make clear the different values. So everywhere on this line is 0.0. It's the center temperature. And everywhere on the surface we have Ts. And remember, we make the assumption it is one-dimensional heat transfer. And the problem also told us we can neglect the heat transfer from there. So it's a very important assumption that was made when we've derived the equations and got to the solution. Right, so let's look at the center temperature of theta 0. What should T0 be equal to? 4. Okay. We want to know how long will it take to decrease the center temperature to 4 degrees Celsius. So that is T0 minus the environment temperature, which is minus 10. Okay, T infinite divided by Ti is the initial temperature, which is 37. 37 minus the environment temperature, which is minus 10. And the result is that theta 0 is equal to 0.2978. Okay? Then also on that graph, you'll see the other thing that we can calculate is 1 divided by the Biot number. And again, the equation is given to us, K divided by HR0. If you're not sure what R0 is, just look on the graph. The graph very specifically, I've removed it now, but you'll see the graph there. But there very specifically it would tell you it is the radius of the cylinder. Okay. So that is equal to K, and K is equal to 0.47 divided by the heat transfer coefficient, which is 22, multiplied by the radius. It's 240 millimeters the diameter, so the radius is equal to 120 millimeters. And the result is a Biot number of 0.177. Okay? So if we now go to figure, and I'm going to go to that figure just now, to figure 4.18a, the Heisler chart. Okay. So on the Heisler chart, there is theta 0, so it's the temperature at 0. That is equal to 0.2978. Okay, and here we look for the Biot number equation, or 1 divided by the Biot number, which should be equal to 0.177. And from that we can get tau. Do you agree? Okay. So please take a look at it for me. So where theta 0 is equal to 0.2978. Can you get it? Okay, so let's go to the graph. Okay, Tamarin, if you can look at that for me. So theta 0, oops. There you go. Okay. So theta 0 is equal to 0.177. I don't know how many of you can get 0.177. Okay. At best, I think you'll get 0.18, 0.2 approximately. You agree? Okay. And then you have to look now for 1 divided by the Biot number, which is equal to 0.177. Again, it would be very difficult to get a line like that. And I think at best you're going to get approximately the line of about 0.2, and you will have to try to get it very accurately. You see? Okay, now when I've tried my best not to be influenced by our previous solution, but I got a tau of about 0.4. You agree? All of you are happy with that? Approximately 0.4? I think our previous solution was 0.3 something. I'm not really sure how many of you can get it to 2 digits. Okay, so now that we've got tau, remember tau is equal to alpha t divided by R0 square. Where do I get it? Well, it is on this axis. They give it to us. It is equal to alpha t divided by R0 squared. It's given there. So tau is equal to 0.4, is equal to alpha, which is equal to 0.13 multiplied by 10 to the minus 6, multiplied by t, that is what we want to solve, divided by the radius. The diameter is 240 millimeters, so the radius is 120 squared. And from it, we can solve the time as 44,308 seconds, and that is about 12.3 hours. Okay. So it's about the same as the previous solution that we got analytically. Does that make sense? You're comfortable with that chart? Okay, now, the other part of the problem was to determine. Okay, now at this time, at 12.3 hours, what would the surface temperature be? because it's a concern, it shouldn't be lower than 0 degrees Celsius. If it is, then we have to change the design parameters. Okay. So at the surface, theta divided by theta 0 is equal to t minus t infinite divided by t0 minus t infinite. So what we want to solve is we want to get that temperature there, the temperature on the surface. Okay. So we need to get theta divided by theta 0. So if we now look at the B part of the graph, you'll see that there we've got theta divided by theta 0. Okay. On this axis, you've got 1 divided by the Biot number. And we already have 1 divided by the Biot number. You see that? And there are different graphs for R divided by R0. Okay. So 1 divided by the Biot number is equal to, we need to get the value here of 0.177. Okay, and then we need to get the right graph. Excuse me. Okay, so R divided by R0 is what we should get. Okay, what is R divided by R0? R divided by R0 is equal to, R is where we want to get the solution, that is R, which is also equal to R0. So R, in this case, we want the solution at 120 millimeters. R0 is a constant, is equal to 0.12, is equal to 1. Okay. So we need to use the line of R divided by R0 is equal to 1. I cannot remember if it's the bottom line or the top one. It doesn't matter. Okay, so one of those lines. So with that, the 1 divided by the Biot number, the position, we can get theta divided by theta 0. Okay. Would you like to try quickly on your chart and see if you can do it? Let me see if I can get it quickly. Okay. So on this chart here on the left, 1 divided by the Biot number is about 0.17. So it is, I don't know if you can see the mouse, it is somewhere there. And there's also the line for about R divided by R0 equal to 1. Okay, the bottom one. You agree? Okay. So you'll see it is not so easy to get a very accurate value from the graph. But I've tried it and I have found it to be about 0.4. Okay, you agree? Approximately 0.4. Okay, so now that we've got theta divided by theta 0 is equal to 0.4, theta divided by theta 0, on this axis, it actually gives you the temperature distribution. It is equal to T minus T infinite divided by T0 minus T infinite. Okay. Okay, so let's do the substitution. It is equal to 0.4 is equal to T minus 10 divided by 37 minus 10. You agree? You all agree? Happy? What is? Yes, yes. Remember, this is again a trap, because we get so used writing this as T minus T infinite divided by Ti minus T infinite. Okay. So this value you can see in this case is equal to T0, the center temperature. Okay. So this shouldn't be 37, it should be 4. The temperature at the center at that time, 12.2 hours. So if we now solve the temperature, let's call it the temperature at the center, Ts, then the temperature at the center is equal to minus 4.4 degrees Celsius. Okay. Previously, I think we got minus 7 point something. Okay. Yep.
The reason for that is theta by theta 0 should be 0.
Okay, so you say it should be 0.2. Okay? Okay. So you immediately see that you've got disagreement about it. Okay. Okay, so obviously if you make it enlarge the picture, it would be easier to get a good solution. But we're talking here of sort of the orders of magnitude. Okay. So, yes, it is definitely not accurate. In some cases, it can be accurate, depending on where the lines are and how far they are apart. But especially when you get to cases when the lines are very close to each other, the resolutions are very small, then obviously it's very difficult to get an accurate solution. Right. Ladies and gentlemen, any questions? Right, so let's continue now with the next part section in the textbook, and that is called Transient Heat Conduction for Semi-Infinite Solids. Okay, SIS, Semi-Infinite Solids. So we've started with simple geometries, now we're going to make it more complex. Then the next part of this complex geometries is called a semi-infinite solid. Now what is a semi-infinite solid? Well, firstly, it is an idealized body. So it's not a real one, of course, but there are many bodies which have this characteristic. Okay. And the first one is the characteristic, it has a single plane surface. It must have a single plane surface. Okay, and then it extends to infinity. On the other surfaces. So if we draw it schematically, it would mean that we do have a surface, and this surface is flat. Okay. And let's suppose that is our coordinate system in the x direction. No, let me use x in that direction, y and z, something like that. And what is now important is that in this direction, in the x direction, it extends into infinity, as well as in the z direction, as well as in the y direction. So it is a large body. And the core temperature, Ti, the core temperature is constant. Okay? And at T equals 0, we have the surface temperature, which is Ts, which is a constant. So we've got a big body, and it has a flat surface here. Its temperature is a constant, Ti, and then suddenly on the surface, the temperature changes. Who of you can think of a body like that? What type of body do you think would be equal to that? Well, the typical applications of this is, for example, close to the surface of the Earth. Close to the surface of the Earth. What are the practical applications? It would be water lines, underground, services, etc. as a typical practical application for that. The second one would be a region relatively close to a surface, a region close to a surface. Now what does that mean? It would mean that if we go to this body here, okay, this body here, we will look at this direction and say, but this is definitely not infinite. Do you agree? Okay. However, if you're interested in the temperature 0.001 millimeters away from the surface, then this dimension 0.001 in comparison with 240 is small. Then you can make an assumption like that. Okay. So with any big body, and again big is relative, close to the surface, this wall, for example, this wall is maybe 300 millimeters thick of this lecture venue. However, if we're interested in how the temperature changes in the wall, when suddenly we change the environment temperature and we want to know just the first few millimeters or microns in the wall, then this approach is valid. Okay. And then thirdly, when we have short periods of time, So again, the wall, when we have it change very quickly and we just want to know the first few seconds what happened. Again, with a beef carcass, just the first few seconds, then the semi-infinite solid approach would be valid. And then thirdly, it would actually mean, in principle, if we look at the Biot number, which is the ratio of conduction to convection, okay, it would mean for very large Biot numbers. The Biot numbers are very, very large. There's a lot of resistance in the body. It doesn't change its temperature very quickly. Changes occurs relatively slow. Then this approach would be very valid. And then the other application for semi-infinite solid is laser treatments. If a laser is being used maybe for treatment on your skin, then you can also make the assumption of a semi-infinite solid because it happens only on the surface or very close to the surface. So the approach that we're going to follow in terms of this big body, let's just look at the mathematics. What is the background before we get to the solution? It starts with, again, looking, of course, at the energy equation from first principles. If we look at the application of the energy equation on this body, then we can say it is equal to ddx of k dt dx plus ddy of k dt dy plus ddz of k dt dz plus E gen is equal to rho c partial dt dt. The one t temperature and the other small t time. So that is the energy equation from first principles. Now the heat transfer again. This body is very, very big and we only change the surface of it. Then we are looking at one-dimensional heat transfer. Typically maybe in the x direction or the y direction only. So let's suppose it is in the x direction. Okay, maybe my x should have been there rather. Okay. So let's change it. It is in the x direction. Okay, so it would mean that those two terms are equal to 0. There's no heat transfer in the y and z directions. There is no energy which is being generated on the inside of the body. There's no nuclear reaction. There's no electrical resistance element. Okay, and obviously this term is now important because we want to know how does the temperature changes as a function of time. So we end up with this equation, and we make the assumption, or we are looking at bodies where the K is a constant. Thermal conductivity is a constant in the x direction. You get bodies, for example, composite materials, where this thermal conductivity would vary in the different directions, and then you cannot make this assumption. But in this case, we can make that assumption, and the result would be that we end up with this partial differential equation, d2t dx squared is equal to rho c divided by k multiplied by partial dt dt is equal to 1 divided by the thermal diffusivity multiplied by partial dt dt. Okay, and we have derived that equation previously when we've started with paragraph 4.2. You all happy with that equation? Right. So, again, to solve it, we need certain boundary conditions. The boundary conditions would be, if we look at the temperature as a function of time, then where x is equal to 0, the temperature would suddenly be equal to Ts. Where x is equal to 0 is on the surface. There the temperature is equal to Ts. That's the first boundary condition. The second boundary condition, also from a geometrical point of view, is equal to the point where x is equal to infinite. So very deep into the body, as function of T, the temperature remains at Ti. The source temperature remains constant, for example, the Earth. If suddenly something happens here on the surface, it doesn't change the core temperature. Okay. And then thirdly, we've got an initial condition, IC1. And that initial condition would be in terms of time, of course. And that would be when time is equal to 0, then we have Ti. Okay, now to solve this, we have to look at the separation of variables method. And we have to convert this partial differential equation into an ordinary differential equation. And this is done by making use of a similarity variable. Now that is why it is important to work through the mathematics. Okay. Because if you just look at the solution, now you're going to see symbols that you do not understand where it comes from. Okay. So we define a similarity variable, which is eta, and this eta is equal to x divided by 4 times the square root of alpha t. I think I've made an error here somewhere. I see I've got a 4 here. I don't think that's correct. Okay. Doesn't matter what that is now. So that is the similarity variable. And take note, it is a function of x and t. A function of x and t. And what we then can do is we can write this partial differential equation as an ordinary differential equation, so that the solution is equal to minus 2 times eta multiplied by dt d eta, and let's call that equation 1. Okay. We're not going to use it immediately, so it doesn't really matter what it is. There's just, I know there's a typo there. Okay. Okay. So if we now look at these boundary conditions, and we also use this similarity variable in terms of that to look at our boundary conditions and rewrite them, then we can end up with a first order differential equation, which can be solved by the separation of variables method. And the result of that is equal to a solution looking like this: T minus Ts divided by Ti minus Ts is equal to 2 times the square root of pi multiplied by the integral of 0 to eta e to the minus u square du. Okay, now what is u? That is just something which is being used to solve this integral. And this integral, there's no exact analytical solution for it. It has to be solved numerically. And the solution of that is equal to what is called ERF, the error function in eta. Okay. And you have an error function and you have a complementary error function. And this is also equal to 1 minus the complementary error function. Okay, Okay, so take note, there's a C indicating the complementary error function. And that is equation 443 in your textbook. Okay, so there's no analytical solution for that. The solution is available. You can do it numerically. I think many of you can do it on your computer. But if you do not have it, in table 4.4 in your textbook, I'm going to show it to you just now. If you go and look at table 4.4, the error function in eta is given there. Okay, if I now look very quickly, I think, is that the correction? It should be? Is it now right? Yeah, there you go. Okay, so that is the correct error function. And here's now the solution for it. So if we look in table 4.4, for different values of eta, then it gives, in this case, the complementary error function, not the error function, the complementary one. Okay. And here for different values of eta, if it is equal to 0, for example, then the complementary function is equal to 1. Okay. And if it is equal to 0.5, it is equal to 0.4795. Okay. And typically at a value of 1, it is equal to 0.1573. And if you keep on looking at it, you will see typically at 3.6, what happens at 3.6? It is equal to 0. Okay. Now you will wonder now, so, I mean, I can look at a table. You don't have to give me these values. It's not so important. This is a very, very important result. Because when I'm going to give you problems to solve in the test and exam, in some cases you're going to end up with quite a complicated formula that you will have to solve in terms of this error function. Okay. And it will have different terms. And the easy solution in many cases is somebody that observes what is going on there. Because it will be very easy to see that in some cases your eta is very high. If you've got a very large value. And if you have a very large value, it is going to help you to know that that term, which is going to be a long term in your equation, is equal to 0. And it's going to save you a lot of time. So take note of this very important thing. You know, if eta becomes large, then the complementary error function is equal to 0. It's really going to help you a lot. Now, this solution is very important now in terms of, let's suppose that this is a semi-infinite solid, and that is now as a function of x. So that is equal to the surface that I'm drawing now. So what we can do with this solution is we can get at different points x, and as a function of t, we can get the solution. Okay. What we can also get is the heat flux, and the equation for that is also given in your textbook. And the heat flux is equal to the heat transfer rate divided by the surface area. So in many cases we rather write down the heat flux as the total heat transfer rate. So the heat flux is equal to how much heat transfer there will be for every square meter. So that is the heat transfer rate going out of that surface, and that would be the area that we're using. Okay. Now I'm not going to do the derivation for you, but it's given there, and because of time I'm just going to write it down now. The result of it looks like this. Okay? Right. So that is now, take note, the solution for this one case. In your textbook there are solutions for, I think, 4 cases. If we can just look at that. Okay, so before we do that, let's just look at the graph. There again is the graph of the complementary error function as a function of eta for different non-dimensionalized times. Okay. And then there are 4 solutions, different cases, where the boundary conditions here, if we can just come back to these boundary conditions, Tamarin, are different. So 4 different solutions. If we go back to the solutions again, you will see the case 1 is the specified surface temperature, Ts is constant. Okay? The second one is where the heat flux is constant on the surface. So that would be on the surface where maybe you have a heater, and you know you're heating the surface at 1 kilowatt per square meter. Or it can be the radiation from the sun, maybe 1,000 watts per square meter. Okay, so that would be that solution. The third one would be the convection on the surface. The wind is blowing over the surface. There's a convection heat transfer, and the heat transfer coefficient is given, or you can get it. And the third one is where you've got an energy pulse, for example, a laser. The laser would give ES a certain number of watts for us. And that would be the 4 different solutions. Any questions, ladies and gentlemen? With the next lecture, we will do an example, and I hope that would make it clear to you. Thank you very much, and enjoy the rest of your day.